What if the very fabric of reality is far stranger than we've ever imagined? What if the rules of space and time, as we know them, are not just bending but breaking in ways that defy logic? Today, we're diving into the mind-bending world of space-time paradoxes, those puzzling contradictions that have left even the brightest scientists scratching their heads. These aren't just thought experiments or science fiction ideas, they are real challenges to our understanding of the universe. From the mysteries of black holes to the enigma of time travel, these paradoxes force us to question everything we think we know about reality. Why do these paradoxes matter? Because they push the boundaries of science, revealing gaps in our knowledge and sparking debates that could one day reshape our understanding of existence. So, buckle up as we explore 20 of the most baffling space-time paradoxes that keep physicists awake at night and might just leave you questioning the nature of reality itself. Now, let's step into one of the most famous and intriguing paradoxes of all time, the grandfather paradox. Imagine this: a time traveler goes back in time and, for whatever reason, ends up preventing their own grandfather from meeting their grandmother. If that happens, the time traveler's parents would never be born, and neither would the time traveler. But if the time traveler doesn't exist, who went back in time to stop their grandparents from meeting in the first place? This mind-bending scenario challenges our understanding of cause and effect, suggesting that time travel could create impossibly tangled loops of logic. Scientists and philosophers have debated this paradox for decades, grappling with questions about the nature of time. If time travel were possible, would the universe somehow prevent such contradictions from happening? Some theories propose that events would realign themselves to avoid paradoxes, while others suggest that alternate timelines or parallel universes could resolve the issue. This paradox has also captured the imagination of popular culture, appearing in countless movies, books, and TV shows, where it often serves as a cautionary tale about meddling with the past. The grandfather paradox isn't just a fun thought experiment, it's a serious challenge to our understanding of causality and the very structure of time. It forces us to confront profound questions. Can the past be changed? Are our actions predestined? Or do we have the power to alter history? These questions remain unanswered, but they continue to inspire both scientific inquiry and creative storytelling, reminding us just how mysterious and complex the universe truly is. Now, shifting our focus, let's dive into another fascinating paradox that defies our understanding of time and causality: the Bootstrap Paradox. Picture this: a time traveler goes back in time and hands Beethoven a complete set of his own symphonies. Beethoven, amazed by the music, publishes it as his own work. Centuries later, the time traveler discovers these symphonies, memorizes them, and travels back to give them to Beethoven. But here's the twist: where did the music originally come from? It seems to have no true origin, existing in an endless loop with no clear beginning. This paradox challenges the very foundation of cause and effect. If an object or piece of information can exist without a creator or source, what does that mean for our understanding of how the universe operates? It raises questions about free will as well. If the time traveler's actions are predestined to create the loop, do they truly have the freedom to choose differently? Or is every event in the timeline fixed, leaving no room for variation? The Bootstrap Paradox also forces us to reconsider the nature of creativity and originality. Could every idea, invention, or piece of art we think of as original actually be part of a loop we're unaware of? It's a concept that has inspired countless works of fiction, where characters grapple with the implications of their actions in a seemingly predetermined timeline. While this paradox remains a theoretical puzzle, it invites us to think deeply about the mechanics of time and the potential consequences of interfering with it. Could such loops exist in reality, or are they merely products of our imagination? As we continue to explore the mysteries of space-time, the Bootstrap Paradox serves as a reminder that the universe might hold secrets far stranger than we can currently comprehend. Now turning to another mind-bending paradox, let's explore the twin paradox, a fascinating thought experiment rooted in Einstein's theory of relativity. Imagine two identical twins. One stays on Earth while the other embarks on a journey through space at a speed close to the speed of light. When the traveling twin returns, they find that they have aged significantly less than their sibling who remained on Earth. How is this possible? This paradox arises from the principles of special relativity, which state that time passes differently for objects in motion compared to those at rest. As the traveling twin moves at near light speed, time slows down for them relative to the twin on Earth, a phenomenon known as time dilation. This isn't just a theoretical concept, it's been confirmed through experiments. For instance, atomic clocks on airplanes or satellites tick slightly slower than those on the ground, and particles accelerated to high speeds in particle colliders experience time at a different rate. What makes the twin paradox so significant is its practical implications for understanding how time operates in our universe. It reveals that time isn't a fixed, universal constant, but rather a flexible dimension influenced by speed and gravity. Think about the future of space travel. Astronauts traveling at relativistic speeds could return to Earth to find that decades or even centuries have passed for those they left behind. This paradox also underscores the interconnected nature of space and time, a cornerstone of modern physics. While it might seem like science fiction, the twin paradox is a real phenomenon with profound implications for our understanding of the cosmos. It challenges our everyday experiences of time and forces us to grapple with the strange, counterintuitive nature of the universe. As we continue to push the boundaries of space exploration, this paradox reminds us that the reality of time is far more complex than it appears. Now shifting our gaze to the stars, we encounter the Fermi Paradox, one of the most intriguing mysteries in the search for extraterrestrial life. Given the vastness of the universe and the high probability of life-sustaining planets, why haven't we found any evidence of intelligent civilizations? This question, posed by physicist Enrico Fermi, highlights a striking contradiction. If life is likely to exist elsewhere, where is everyone? One compelling explanation is the Great Filter theory, which suggests that there's a barrier preventing life from advancing to the point of interstellar communication or travel. This filter could occur at any stage. Perhaps the leap from simple to complex life is incredibly rare, or advanced civilizations inevitably self-destruct. If the Great Filter lies in our past, humanity might have already beaten the odds. But if it lies ahead, our future could be uncertain. Another theory is the rare Earth hypothesis, which argues that Earth-like planets with the right conditions for complex life are exceptionally uncommon. Factors like a stable star, the right distance from it, and a protective magnetic field might be so rare that intelligent life is a cosmic anomaly. This idea suggests that while microbial life might be widespread, civilizations like ours could be exceedingly rare. The Fermi Paradox also raises questions about our methods of searching for extraterrestrial life. Could it be that advanced civilizations communicate in ways we can't detect, or do they simply choose to remain hidden? Some speculate that they might have evolved beyond physical forms or have no interest in interstellar travel. This paradox challenges our understanding of life's place in the universe and forces us to confront profound questions about our existence. Are we alone, or is the cosmos teeming with life we're unable to see? As we continue to explore the stars, the Fermi Paradox reminds us that the universe is full of mysteries waiting to be unraveled. Now delving into the depths of cosmic mysteries, we encounter the black hole information paradox, a puzzle that challenges the very foundations of physics. At the heart of this paradox lies a question: what happens to information when it falls into a black hole? According to quantum mechanics, information can never be truly destroyed. Yet, black holes seem to defy this principle, swallowing everything that crosses their event horizon, including light and matter, and leaving no trace behind. This contradiction was brought to light by physicist Stephen Hawking, who discovered that black holes aren't completely black. They emit a faint radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch. Hawking's calculations suggested that this radiation carries no information about the objects that fell into the black hole. If true, this would mean the information is irretrievably lost, violating a core tenet of quantum mechanics. This paradox sparked a decades-long debate among scientists. One proposed solution is the idea that information might be encoded in the Hawking radiation itself, albeit in a highly scrambled form. Others suggest that information could be stored on the black hole's event horizon in a process known as the holographic principle, where all the data about what falls into the black hole is preserved on its surface. Yet another theory posits that black holes might not evaporate completely, but instead leave behind a remnant containing the lost information. Each of these ideas has its own challenges and implications, and the debate remains unresolved. The black hole information paradox forces us to reconsider our understanding of gravity, quantum mechanics, and the very nature of reality. As scientists continue to explore this enigma, one thing is certain: black holes hold secrets that could reshape our comprehension of the universe. Now shifting our focus to the quantum realm, we encounter the Einstein-Podolsky-Rosen Paradox, a mind-bending puzzle that questions the very fabric of reality. This paradox revolves around entangled particles, pairs that are so deeply connected that the state of one instantaneously influences the other, no matter how far apart they are. At first glance, this seems to violate the principle of locality, the idea that an object is only directly influenced by its immediate surroundings. The paradox was first proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 as a way to challenge the completeness of quantum mechanics. They argued that if quantum mechanics were truly complete, it would allow for what Einstein famously called spooky action at a distance, where particles appear to communicate faster than the speed of light. This, they believed, defied the rules of relativity and suggested that there must be some hidden variables at play, factors not accounted for in the quantum theory. To understand why this is so puzzling, imagine two entangled particles separated by vast distances. If you measure the state of one particle, the other instantly assumes a corresponding state, seemingly without any time delay. This instantaneous connection appears to bypass the speed of light, the cosmic speed limit set by Einstein's theory of relativity. But here's the twist: this doesn't actually allow for faster-than-light communication. While the particles are correlated, no useful information is transmitted between them, leaving the paradox intact. The implications of this paradox are profound. It forces us to reconsider the nature of reality itself. Are particles truly connected across vast distances, or is there a deeper, hidden layer to the universe that we haven't yet uncovered? Experiments over the years, such as those based on Bell's theorem, have shown that entangled particles do indeed exhibit this strange behavior, ruling out the possibility of local hidden variables in most interpretations. The Einstein-Podolsky-Rosen Paradox remains a cornerstone of quantum mechanics, challenging our understanding of space, time, and causality. It invites us to explore the boundaries of what we know and to question whether reality is as straightforward as it seems. As we continue to probe this mystery, we may uncover insights that reshape not only our understanding of physics, but also our perception of the universe itself. Now venturing into the realm of cosmic oddities, we encounter the Boltzmann Brain Paradox, a thought experiment that challenges our understanding of reality itself. This paradox arises from the idea that in a universe governed by random fluctuations, a fully self-aware brain could spontaneously form out of nowhere. Picture this: in the vast, chaotic expanse of the cosmos, atoms and particles could, purely by chance, arrange themselves into a functioning brain complete with memories and thoughts. even though it has no physical body or history. The paradox is named after Ludwig Boltzmann, a physicist who explored the role of entropy and randomness in the universe. It stems from the concept that, given enough time, even the most improbable events can occur. In an infinite or near-infinite universe, the odds of a self-aware brain forming randomly might seem vanishingly small, but they're not zero. This raises the unsettling question, could we, right now, be such brains, imagining the entire universe and our place in it? The implications of this paradox are profound, especially for cosmology. If the universe lasts long enough, or if there are infinite universes, the likelihood of Boltzmann brains forming increases. This challenges our understanding of what is real and what is an illusion. Are we truly the product of billions of years of cosmic evolution, or are we just fleeting moments of consciousness in an otherwise chaotic void? What makes this paradox both fascinating and deeply unsettling is its connection to the nature of consciousness. It forces us to confront the possibility that our sense of self and our perception of reality could be entirely accidental constructs. This paradox also ties into the anthropic principle, which suggests that the universe must be compatible with the existence of observers like us. But if Boltzmann brains are possible, the very nature of observation and consciousness becomes a cosmic enigma. While this paradox may seem like a mere philosophical curiosity, it has serious implications for our understanding of the universe. It pushes scientists to refine theories about the nature of time, entropy, and the structure of reality itself. It also serves as a reminder of how much we still don't know about the cosmos and our place within it. As we grapple with this paradox, we are reminded that the universe is far stranger and more mysterious than we often imagine. Now shifting our focus to the quantum realm, we encounter the Wheeler's delayed choice paradox, a mind-bending concept that challenges our understanding of time and causality. Named after physicist John Wheeler, this paradox explores how an observer's decision in a quantum experiment can appear to influence events that have already happened. Imagine this: particles like photons behave differently based on whether they are being observed or not. In a classic double-slit experiment, photons can act as both particles and waves, but the act of measuring them forces them to choose one behavior. The twist in Wheeler's paradox comes when the decision to measure or not measure these particles is made after the particles have already passed through the slits. It's as if the observer's choice in the present can retroactively determine the particle's behavior in the past. This raises a startling question. Does the present influence the past, or does our understanding of time need to be fundamentally rethought? At its core, this paradox highlights the strange and counterintuitive nature of quantum mechanics. It suggests that reality may not be as fixed and objective as we once thought. Instead, the act of observation might play a crucial role in shaping what we perceive as real. This challenges the classical view of causality, where cause always precedes effect. Here, it seems as if the effect can reach back in time to influence the cause. The implications of this paradox are profound, not just for physics, but for our understanding of existence itself. It forces us to consider whether the universe is deterministic or if it's shaped by our observations. Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that reality only becomes definite when observed. Others, like the many worlds interpretation, propose that every possible outcome exists in parallel universes, sidestepping the paradox altogether. What makes Wheeler's delayed choice paradox particularly intriguing is its connection to the nature of time. It suggests that time might not flow in a straightforward, linear way, but could be far more fluid and interconnected than we realize. This paradox also underscores the mysterious relationship between the observer and the observed, blurring the line between the subjective and the objective. As scientists continue to grapple with this paradox, it serves as a reminder of how much we still have to learn about the universe. It pushes the boundaries of our understanding, inviting us to question the very fabric of reality. Whether time is malleable, observation is fundamental, or our entire framework of physics needs revision, the Wheeler's delayed choice paradox remains one of the most fascinating and perplexing puzzles in science. Now stepping into the realm of one of quantum mechanics' most iconic thought experiments, we encounter the Schrödinger's cat paradox. Introduced by physicist Erwin Schrödinger in the 1930s, this paradox is designed to highlight the bizarre nature of quantum superposition. Here's the scenario. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If it doesn't decay, the cat remains alive. According to quantum mechanics, until the box is opened and observed, the atom exists in a superposition of decayed and not decayed states. This means the cat is simultaneously alive and dead. At first glance, this seems absurd. How can a cat be both alive and dead at the same time? The paradox serves as a metaphor for the strange behavior of particles at the quantum level, where they can exist in multiple states until measured. It's a powerful illustration of the concept of wave function collapse, where the act of observation forces a quantum system to choose a definite state. Before observation, the system is a blur of possibilities. After observation, it's one concrete reality. Schrödinger's cat also challenges our everyday understanding of reality. It forces us to confront the idea that the universe doesn't operate in the straightforward, deterministic way we experience in our macroscopic world. Instead, it suggests that reality is probabilistic and that observation plays a crucial role in shaping it. This paradox has sparked debates for decades, with interpretations ranging from the Copenhagen interpretation, which emphasizes the role of the observer, to the many worlds interpretation, which proposes that every possible outcome branches into a separate universe. What makes this paradox particularly striking is how it bridges the gap between the microscopic world of particles and the macroscopic world we live in. It's one thing to accept that an electron can be in two places at once, but applying that logic to a living creature like a cat is both unsettling and thought-provoking. It challenges us to rethink our assumptions about life, death, and the nature of existence itself. As we continue to explore the implications of Schrödinger's cat, it's clear that this paradox is more than just a clever thought experiment. It's a window into the profound mysteries of quantum mechanics, reminding us that the universe is far stranger than we can imagine. Whether the cat is alive, dead, or both, this paradox keeps us questioning the very fabric of reality. Now shifting our focus to the relentless march of time, we encounter the arrow of time paradox. At its core, this paradox asks a simple yet profound question. Why does time move only forward, even though the fundamental laws of physics don't seem to care about direction? In other words, if you could reverse a physical process like a ball rolling down a hill, the equations that describe it would still hold true. Yet in our everyday experience, time flows in one direction and we can't rewind it. One of the leading explanations for this paradox lies in the concept of entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy in a closed system always increases over time. This means that as time progresses, things naturally tend to become more disordered, like a cup of coffee cooling down or a shuffled deck of cards. The increase in entropy appears to give time its direction, like an arrow pointing from order to chaos. But this raises another question. Why was the universe in such a low entropy, highly ordered state at the beginning? Many scientists point to the Big Bang as the starting point. The universe began in an incredibly dense and hot state with extremely low entropy. From there, it expanded and cooled, leading to the increase in entropy we observe today. This explains why time seems to move forward, but it also leaves us with a deeper mystery. What caused the universe to start in such a specific, low-entropy condition? Despite these insights, the arrow of time paradox remains unsolved. While entropy provides a compelling explanation, it doesn't fully account for why time behaves the way it does. Some theories suggest that the arrow of time might be linked to the expansion of the universe itself, while others propose that it could be tied to the nature of consciousness or even the quantum realm. What makes this paradox so fascinating is its universality. Time's one-way flow affects everything from the life cycle of stars to the aging of our own bodies. It's a reminder that, while the laws of physics may be time-symmetric, our experience of time is anything but. As we continue to probe this mystery, the arrow of time paradox challenges us to rethink our understanding of the universe and our place within it, leaving us to wonder, is time's direction an intrinsic property of reality, or is it something we impose through our own perception? Now diving into the strange world of quantum mechanics, we encounter the quantum Zeno paradox. This paradox suggests that simply observing a quantum system can prevent it from changing, almost as if it's frozen in time. Imagine watching a pot of water on the stove. If you keep checking it every second, it might never boil. In the quantum realm, this idea becomes even more bizarre. When scientists repeatedly measure a quantum system, they can effectively halt its natural evolution. This phenomenon is named after Zeno of Elea, an ancient philosopher who argued that motion is an illusion because at any given moment an object is at rest. While Zeno's paradoxes were dismissed in classical physics, in the quantum world, something eerily similar happens. The key to understanding this paradox lies in the way quantum systems behave. Unlike the everyday objects we're familiar with, quantum particles exist in a state of superposition, meaning they can be in multiple states at once until they're observed. When you measure a quantum system, it collapses into one definite state. If you measure it again and again in rapid succession, it doesn't have time to evolve, effectively freezing it in place. This effect has been demonstrated in experiments, showing that frequent observation can slow down or even stop the decay of unstable particles. But what does this mean for our understanding of reality? The quantum Zeno paradox challenges the very nature of observation and its role in shaping the universe. It suggests that the act of measuring isn't just a passive process but an active one that can influence the behavior of the system being observed. This raises profound questions about the relationship between consciousness and reality. Could the observer be a fundamental part of the fabric of the universe? While the paradox doesn't provide definitive answers, it forces us to rethink our assumptions about how the quantum world operates. Beyond its philosophical implications, the quantum Zeno paradox has practical applications as well. In quantum computing, for example, controlling the evolution of quantum states is crucial. By leveraging the principles of this paradox, researchers can design systems that maintain their coherence for longer periods, paving the way for more powerful quantum technologies. Yet, even as we harness its potential, the paradox continues to perplex scientists, reminding us that the quantum realm is full of mysteries waiting to be unraveled. As we explore this paradox, we're left with a deeper appreciation for the strange and counterintuitive nature of quantum mechanics. It's a reminder that, in the quantum world, the simple act of looking can have profound consequences, challenging our understanding of time, change, and the very fabric of reality. Now shifting our gaze to the cosmos, we encounter Olbers' paradox, a question that has puzzled astronomers for centuries. Why is the night sky dark? If the universe is infinite and filled with an endless number of stars, shouldn't every point in the sky glow as brightly as the surface of a star? This paradox, named after the German astronomer Heinrich Wilhelm Olbers, challenges our understanding of the universe's structure and its history. On the surface, it seems logical that an infinite number of stars should light up the entire sky, but reality tells a different story. The key to unraveling this mystery lies in two crucial factors: the expansion of the universe and the finite age of stars. First, the universe is not static, it's expanding. This means that light from distant stars is stretched into longer, redder wavelengths as space itself stretches, a phenomenon known as redshift. Over vast distances, this stretching can shift visible light out of our detectable range, effectively dimming the star's brightness. Second, the universe has a finite age around 13.8 billion years. This means that light from stars beyond a certain distance hasn't had enough time to reach us yet. These two factors combine to explain why the night sky isn't ablaze with starlight. However, even with these explanations, Olbers' paradox remains a classic because it highlights deeper questions about the nature of the universe. For instance, if the universe were truly infinite and unchanging, the paradox would still hold. The fact that it doesn't suggest that our understanding of the cosmos is incomplete. It also underscores the importance of considering both the universe's age and its dynamic nature when studying its properties. Beyond its theoretical implications, Olbers' paradox has practical significance in modern astronomy. It reminds us that the universe's observable boundaries are shaped by the speed of light and the time since the Big Bang. This paradox has also inspired further exploration into the distribution of matter in the universe and the effects of cosmic expansion on our observations. While the paradox has largely been resolved, it continues to serve as a thought-provoking example of how even the simplest questions can lead to profound insights about the cosmos. As we reflect on Olbers' paradox, we're reminded that the darkness of the night sky is more than just an absence of light. It's a window into the universe's history and structure. It's a testament to the complex interplay of time, space, and light, inviting us to keep exploring the mysteries that lie beyond our reach. Now shifting our perspective to the boundaries of speed and causality, we arrive at the superluminal paradox, a mind-bending concept that explores the implications of faster-than-light travel. Imagine a scenario where a spaceship could move faster than the speed of light. At first glance, this might seem like an exciting breakthrough, but it quickly unravels into a web of contradictions that challenge our understanding of physics. The heart of this paradox lies in the principle of causality, the idea that cause must always precede effect. If faster-than-light travel were possible, it could lead to situations where effects occur before their causes, creating a logical inconsistency. For example, consider a scenario where you send a message to a distant star system faster than light. In theory, the message could arrive before you even send it, effectively allowing the recipient to respond to something that hasn't happened yet. This so-called tachyonic antitelephone scenario is one of the most striking examples of how faster-than-light travel could disrupt the flow of time and cause paradoxes. But why does this challenge our understanding of physics so profoundly? At its core, the dilemma stems from Einstein's theory of relativity, which establishes the speed of light as the ultimate speed limit in the universe. According to relativity, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to reach or surpass that limit. Faster-than-light travel would not only break this fundamental rule, but also introduce inconsistencies in the fabric of space-time, making it difficult to reconcile with our current understanding of the universe. Interestingly, this paradox isn't just a theoretical curiosity, it has practical implications for our exploration of the cosmos. If faster-than-light travel were possible, it would open up the possibility of interstellar travel and communication across vast distances. However, the accompanying paradoxes suggest that there may be deeper laws of physics preventing such possibilities. This raises profound questions about the nature of reality and whether the universe has built-in safeguards to preserve the integrity of cause and effect. As we ponder the superluminal paradox, we're reminded of the delicate balance that governs the cosmos. While the idea of breaking the light barrier is tantalizing, the paradoxes it creates serve as a humbling reminder of the limits imposed by the natural world. It's a testament to the intricate interplay of space, time, and causality, urging us to continue questioning and exploring the mysteries of the universe. With each paradox we encounter, we edge closer to a deeper understanding of the fabric of reality. Now delving into the realm of infinite possibilities, we encounter the multiverse paradox, a concept that stretches the boundaries of our imagination and challenges our understanding of reality. Picture a universe where every decision, every event spawns a new reality, creating an infinite web of parallel worlds. In this multiverse, there could be countless versions of you, each living a slightly different life based on the choices they've made. While this idea is fascinating, it also raises profound questions about identity, free will, and the nature of existence. At its core, the multiverse paradox forces us to confront the idea that every possible outcome of every event exists somewhere in the vast expanse of reality. This means that somewhere out there, there's a version of you who took a different path in life, achieved different goals, or even made entirely opposite decisions. While this might sound liberating, it also introduces a paradox. If every possible version of you exists, does that mean your choices truly matter, or are they just one thread in an infinite tapestry of realities? The implications of the multiverse extend beyond personal identity. It also challenges our understanding of free will. If every decision leads to a new universe, does that mean we're destined to make every possible choice at some point? Or do we retain the power to shape our own destiny within our individual reality? These questions blur the line between determinism and free will, leaving us to wonder whether we're the architects of our lives or merely players in a cosmic game of chance. Moreover, the multiverse paradox invites us to rethink the nature of reality itself. If an infinite number of universes exist, each with its own set of physical laws and constants, what does that say about the uniqueness of our own universe? Are we just one of countless realities, or is there something special about the conditions that allowed life to emerge here? This paradox doesn't just challenge our understanding of the cosmos, it forces us to reconsider our place within it. As we explore the multiverse paradox, we're reminded of the vastness of the unknown and the limitations of our current knowledge. While the idea of infinite realities is both thrilling and unsettling, it also serves as a powerful reminder of how much we have yet to discover. It's a paradox that invites us to keep questioning, keep exploring, and keep pushing the boundaries of what we think is possible. With each new insight, we edge closer to unraveling the mysteries of existence itself. Shifting our gaze to the cosmic enigma of black holes, we encounter the Hawking radiation paradox, a phenomenon that turns our understanding of these mysterious objects on its head. Black holes, once thought to be the ultimate cosmic vacuum cleaners, pulling in everything and letting nothing escape, were redefined by the groundbreaking work of Stephen Hawking. He proposed that black holes are not entirely black after all. They emit a faint form of radiation, now known as Hawking radiation. This discovery was revolutionary, but it also opened the door to a puzzling paradox. If black holes emit radiation and eventually evaporate, what happens to all the information they've swallowed? At first glance, this might seem like a simple question, but it strikes at the heart of one of the most fundamental principles of physics, the conservation of information. In the quantum world, information is never truly lost. It can be scrambled or transformed, but it's always preserved in some form. Yet, Hawking's theory suggests that as black holes emit radiation and shrink, the information about the matter they've consumed might be irretrievably lost. This idea directly challenges our understanding of quantum mechanics and raises a troubling question. Does the universe have a memory, or can information simply vanish into the void? The Hawking radiation paradox is deeply intertwined with the black hole information paradox, a debate that has divided physicists for decades. Some scientists, including Hawking himself, initially believed that information could indeed be lost forever in black holes. However, this view was met with widespread skepticism, as it seemed to violate the core tenets of quantum theory. Over time, alternative ideas emerged, such as the holographic principle, which suggests that all the information about what falls into a black hole is somehow encoded on its surface rather than being lost. This idea paints black holes as cosmic holograms, storing information in ways we're just beginning to understand. The debate remains far from settled, with physicists continuing to explore new theories and models to resolve the paradox. One intriguing possibility is that information is somehow encoded in the Hawking radiation itself, allowing it to escape as the black hole evaporates. If true, this would mean that black holes are not the information-destroying monsters we once thought, but rather complex cosmic objects that process and release information in ways we're still struggling to comprehend. The Hawking radiation paradox not only deepens our understanding of black holes, but also forces us to rethink the very fabric of reality, blending the strange worlds of quantum mechanics and general relativity. As we grapple with this paradox, we're reminded of the profound mysteries that black holes still hold. They are not just gravitational behemoths, but also cosmic laboratories where the laws of physics are pushed to their limits. The Hawking radiation paradox invites us to keep questioning, keep theorizing, and keep exploring the enigmatic nature of the universe. With each new discovery, we inch closer to unraveling the secrets of these cosmic enigmas and the fundamental principles that govern our reality. Now shifting our perspective to the realm of interstellar travel, we encounter the time dilation paradox, a mind-bending consequence of Einstein's theory of relativity. Time dilation occurs when time passes at different rates for observers in different gravitational fields or moving at different speeds. For example, an astronaut traveling at near light speed would age slower than someone remaining on Earth. This phenomenon, while confirmed by experiments like the famous Hayfel-Keating experiment with atomic clocks, leads to some perplexing scenarios when applied to space travel. Imagine a mission to a distant star system hundreds of light years away. If a spacecraft could travel close to the speed of light, the astronauts might experience only a few years on board while centuries pass on Earth. Upon their return, they would find themselves in a future world vastly different from the one they left behind. This creates a paradox. While the astronauts have aged only slightly, their families, friends, and even entire civilizations might have moved on or ceased to exist. The disconnect between their experienced time and Earth's timeline raises profound questions about the nature of time and the feasibility of interstellar travel. The practical implications of time dilation are immense, particularly for astronauts embarking on long-duration missions. Even within our solar system, astronauts on Mars or other distant destinations would experience slight time differences compared to Earth. Over extended periods, these differences could accumulate, creating challenges for communication, mission planning, and even biological aging. For example, a crew sent to colonize a distant planet might find their biological clocks out of sync with Earth's, complicating everything from medical care to social interactions. The time dilation paradox also poses significant hurdles for interstellar colonization. If humans were to establish colonies in distant star systems, the time differences could lead to cultural and technological divergence. A colony that experiences time at a different rate might develop independently from Earth, potentially leading to a future where humanity is no longer a unified species. Additionally, the vast distances and time disparities would make it nearly impossible to maintain real-time communication or coordination between Earth and its far-flung colonies. Despite these challenges, the time dilation paradox also offers a glimmer of hope. It suggests that traveling to distant stars within a human lifetime might be achievable, at least for the travelers themselves. This could open the door to exploring and potentially colonizing worlds far beyond our solar system. Yet, it also forces us to confront the profound complexities of time, relativity, and our place in the cosmos. As we ponder the implications of this paradox, we're reminded of the intricate interplay between time, space, and human ambition. The time dilation paradox challenges us to rethink our approach to space travel, urging us to consider not just the technical hurdles but also the philosophical and practical consequences of bending the very fabric of time. It's a reminder that the universe operates by rules that often defy our intuition, inviting us to explore, question, and adapt as we venture into the unknown. Now shifting our gaze to the quantum realm, we encounter the observer effect paradox, a phenomenon that challenges our understanding of reality itself. In the world of quantum mechanics, particles can exist in a state of superposition, meaning they can be in multiple states at once until they are observed. The very act of measurement or observation forces these particles to choose a specific state. This raises a startling question: does the observer play a role in shaping reality? The classic example of this paradox is the double-slit experiment, where particles like electrons behave as waves when unobserved, creating an interference pattern. However, when scientists attempt to measure which slit the particle passes through, the wave-like behavior collapses and the particle acts like a single, localized entity. This suggests that the act of observation influences the outcome of the experiment, leading to the profound implication that reality may not exist in a fixed state until it is observed. This paradox has sparked intense debate among physicists and philosophers alike. Some interpret it as evidence that consciousness plays a fundamental role in the universe, effectively creating reality through observation. Others argue that observation in this context simply refers to interaction with the environment, not necessarily conscious beings. Regardless of the interpretation, the observer effect paradox forces us to reconsider the nature of existence and the boundaries between observer and observed. What does this mean for our understanding of the universe? If observation can alter the behavior of particles, then reality itself may be far more fluid and subjective than we once believed. It raises questions about whether the universe exists independently of our perception or if our consciousness is an integral part of its fabric. These ideas push the boundaries of science and philosophy, blurring the lines between physical reality and the mind. The implications extend beyond the quantum world, touching on our everyday experiences. If observation can influence the behavior of particles, could our perceptions and expectations shape the world around us in subtle ways? This paradox invites us to explore the profound connection between consciousness and the cosmos, opening up new avenues of thought about the nature of reality itself. As we delve into this paradox, we're reminded that the universe is far stranger and more interconnected than we often assume. The observer effect paradox not only challenges our scientific frameworks, but also invites us to ponder the deeper mysteries of existence, observation, and the very nature of reality. It's a humbling reminder that the cosmos still holds countless secrets waiting to be uncovered. Delving deeper into the unknown, let's explore the cosmic censorship paradox, a concept that seeks to protect the fabric of our universe from chaos. At the heart of this paradox lies the idea that singularities, such as those found in black holes, are always hidden from our view, shielded by an event horizon. This censorship prevents the bizarre and unpredictable effects of singularities from spilling out into the observable universe, preserving the laws of physics as we know them. But why is this idea so crucial, and what makes it so controversial? The cosmic censorship hypothesis, proposed by physicist Roger Penrose, suggests that nature itself has a built-in mechanism to hide singularities. Without this safeguard, the extreme gravitational forces at a singularity could lead to paradoxes and violations of causality, disrupting the orderly structure of spacetime. For example, a naked singularity, one not hidden by an event horizon, could theoretically allow information or matter to escape in ways that defy our current understanding of physics. However, not all scientists agree. Some argue that the hypothesis is more of a convenient assumption than a proven fact, while the idea of cosmic censorship helps maintain the integrity of our physical laws. There's no definitive evidence that singularities are always hidden. In fact, certain mathematical models and simulations suggest that naked singularities might be possible under specific conditions. If these were to exist, they could challenge our understanding of gravity, space-time, and the very foundations of physics. This debate has profound implications for our understanding of the universe. If singularities are always hidden, it reinforces the idea that the universe operates within a set of consistent and predictable rules. But if naked singularities exist, they could open the door to phenomena that defy explanation, forcing us to rethink the nature of reality itself. The cosmic censorship paradox also raises questions about the limits of our knowledge. Are there aspects of the universe that are fundamentally unknowable, shielded from us by nature's design? Or is this hypothesis simply a placeholder, waiting to be replaced by a deeper understanding of gravity and spacetime? As we continue to probe the mysteries of black holes and singularities, this paradox reminds us that the cosmos is full of surprises, challenging us to question our assumptions and expand our horizons. With this paradox, we're reminded that the universe is not only stranger than we imagine, but also stranger than we can imagine. It's a humbling thought that keeps scientists and thinkers alike on the edge of discovery, always searching for the next piece of the cosmic puzzle. Now turning to a paradox that might make you question the very nature of reality, let's explore the simulation paradox. This idea suggests that our entire universe could be nothing more than an advanced simulation, created by an intelligent civilization far beyond our comprehension. It's a concept that blurs the line between science fiction and scientific possibility, challenging us to rethink what we know about existence itself. The roots of this paradox can be traced back to philosopher Nick Bostrom, who proposed that at least one of the following must be true. Either human civilization is likely to go extinct before reaching a post-human stage. Post-human civilizations are unlikely to run simulations of their ancestors, or we are almost certainly living in a simulation. If the first two possibilities seem unlikely, then the third becomes a startling possibility. But what does it mean to live in a simulation? If our universe is a simulation, then everything we perceive as reality, the stars, the planets, even our own thoughts and emotions, could be lines of code in a vast, intricate program. This raises profound questions about free will, consciousness, and the nature of our experiences. If we're just characters in a simulation, do our choices truly matter, or are they predetermined by the program? The simulation paradox also introduces the idea of nested simulations. If our universe is a simulation, couldn't its creators also be part of a simulation? This leads to an infinite regress where each layer of reality is a simulation within a simulation, making it impossible to determine what, if anything, is truly real. From a scientific perspective, this paradox challenges our understanding of physics and the fundamental nature of the universe. Some researchers have even proposed experiments to test the simulation hypothesis, such as looking for tiny, pixel-like structures in the fabric of spacetime or anomalies in the behavior of particles. Philosophically, the simulation hypothesis forces us to confront questions about the meaning of life and the nature of existence. If we're living in a simulation, does that diminish the value of our experiences, or does it make them even more fascinating? It also raises ethical questions for the hypothetical creators of the simulation. Are they observing us, and if so, what are their intentions? While the simulation paradox remains a speculative idea, it serves as a powerful reminder of how little we truly understand about the universe. It challenges us to think beyond the boundaries of our senses and consider the possibility that reality might be far more complex and far stranger than we ever imagined. As we ponder this paradox, one thing becomes clear. Whether our universe is real or simulated, the questions it raises are undeniably real, pushing us to explore the deepest mysteries of existence. Shifting our perspective to a mind-bending idea that bridges quantum mechanics and the concept of immortality, let's dive into the quantum immortality paradox. This thought experiment suggests that in a universe governed by quantum mechanics, consciousness could theoretically continue indefinitely by branching into alternate realities. Imagine a scenario where every decision or event that could lead to your death simply results in your consciousness shifting to a reality where you survive. In this way, you might never experience death from your own perspective, even if it appears inevitable from an outside view. At the heart of this paradox is the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of a quantum event actually occurs, creating infinite parallel universes. In this framework, your consciousness would always follow the path where you remain alive, no matter how unlikely it seems. For example, if you were to step into a potentially fatal situation, there would always be a universe where you survive, even if the odds are astronomically small. This raises profound questions about the nature of existence and the concept of death. If consciousness can persist indefinitely across alternate realities, does death even exist from the perspective of the individual? It also challenges our understanding of identity, as each survival scenario would create a version of you that diverges further from the original. Are you still you in these alternate realities, or is each version a separate entity? The quantum immortality paradox also blurs the line between science and philosophy. It forces us to consider whether consciousness is tied to the physical body or if it can transcend it in some way. Moreover, it invites speculation about the ultimate fate of the universe. If consciousness can persist indefinitely, could it eventually witness the end of all possible realities, or would it simply keep branching forever? While this paradox remains speculative and largely untestable, it serves as a fascinating exploration of the boundaries between life, death, and the nature of reality. It challenges us to rethink our assumptions about mortality and consider the possibility that existence might be far more complex and enduring than we've ever imagined. As we ponder this paradox, one thing becomes clear: whether or not quantum immortality is possible, it invites us to question the very essence of what it means to be alive and what lies beyond the boundaries of our current understanding. As we wrap up this journey through the mind-bending mysteries of space-time, let's take a moment to reflect on the 20 paradoxes we've explored. From the grandfather paradox to the quantum immortality paradox, each one challenges our understanding of reality, time, and existence. These paradoxes don't just puzzle scientists, they invite all of us to question the very fabric of the universe and our place within it. The complexity of these ideas reminds us that the cosmos is far more intricate and mysterious than we often assume. Whether it's the mind-bending implications of time travel, the eerie possibilities of parallel universes, or the unresolved questions about black holes and quantum mechanics, these paradoxes push the boundaries of human knowledge. They reveal how much we have yet to discover and how much more there is to explore. As you ponder these mysteries, remember that science thrives on curiosity and questioning. Each paradox is a doorway to deeper understanding, a puzzle waiting to be solved. What do you think about these ideas? Do they spark new questions or theories in your mind? Share your thoughts in the comments below. We'd love to hear your perspectives and engage in this fascinating discussion. If you enjoyed diving into these space-time paradoxes, don't forget to subscribe and hit the notification bell for more thought-provoking content. There's a universe of mysteries waiting to be explored, and we're just getting started. Until next time, keep questioning, keep wondering, and keep exploring the endless wonders of the cosmos.